Hey everyone, welcome back. We're about to do a quick review of Chemistry Chapter 15, all about equilibrium. The goal here is to tie everything together, from precipitation to coupled reactions, so you can really see the big picture.
So have you ever looked at something like this, these amazing fluoride crystals, and wondered, how in the world does that even form? Well, it's not magic, it's pure chemistry. And that's exactly what this chapter is all about. The whole process, ions in the water just coming together to make something solid, it's a perfect example of what we're talking about, that constant dance between precipitation and dissolution.
All right, here's our game plan. We're going to start with the absolute fundamentals, the key terms and equations you gotta know. Then, we'll walk through the summaries for each section to see how those building blocks are actually used. And finally, we'll wrap it all up to give you that complete bird's-eye view of the chapter. Okay. Before we get into the nitty-gritty, we have to make sure we're all on the same page, speaking the same language. These key terms are seriously the foundation for everything else, so getting these down is absolutely crucial. Here's our first batch of vocab. What's really interesting is how some of these terms, like the common ion effect or coupled equilibria, already give you a hint that none of these reactions are happening in a vacuum. They all influence each other. I'm not going to read every single one, so this is a great time to hit pause and just get familiar with these ideas.
And here is our second set of terms. Now, the Lewis acid-base stuff is super important, but the one you are going to see again and again and again is the solubility product constant, or KSP. Trust me, this is the key to predicting if a solid will actually form or not. It's a huge deal in geology, medicine, you name it. So again, go ahead and pause here if you need to.
Okay, so we've got the words down, now let's see how they get turned into math. These equations, especially the one for KSP, are the tools that let us go from just talking about equilibrium to actually making precise quantitative predictions.
I know this equation looks a little intimidating at first glance, but let's break it down. It's really just a generic way of showing a solid dissolving. On the left, you have your solid compound, M sub P, X sub Q. On the right, you have the separate ions it breaks into when it's in a solution. And that double arrow in the middle? That's the whole point. It means the process is reversible. It's a true equilibrium.
And here it is, the mathematical heart of this chapter, the solubility product constant, KSP. All you're doing is multiplying the concentrations of the dissolved ions. And it's so powerful. A really small KSP value means you're going to have a lot of solid and not very many dissolved ions. In other words, it's not very soluble. It's a simple, elegant way to put a number on solubility.
So now we've got our basic tools, the vocab and the equations. Let's see how they actually get put to work in the three main sections of the chapter. We'll just run through the summary of each one to really connect the dots.
First up is section 15.1. This is all about that push and pull. Solids forming out of a solution, which is precipitation, and then dissolving right back into it.
And big surprise, the star of this section is our old friend, the KSP expression. This little constant is the key to unlocking basically everything you need to know about solubility.
So this section really shows you what KSP can do. You can use it to figure out a compound's molar solubility, and you can even work backward. If you know the solubility, you can find the KSP. But the really cool part is when you compare KSP to the reaction quotient, Q. If Q is bigger than KSP, then boom, you know for sure a solid is going to precipitate. It's like having a chemical crystal ball. All right, moving on to section 15.2. Here, the chapter takes what we know about acids and bases and just blows it wide open with the Lewis model. It's all about electron pairs now.
So this section gives us a much broader definition. A Lewis acid? It's simply an electron pair acceptor, and a Lewis base is an electron pair donor. A classic example is a complex ion. You've got that central metal ion that really wants electrons. That's your Lewis acid. And the ligands all around it are happy to donate their electrons, acting as Lewis bases. And finally, section 15.3. This is where we really bring it all home by looking at coupled equilibria. This is where you see how complex and powerful all of this can be when reactions start interacting with each other. This is where it all clicks. Think of coupled equilibria as like a chemical chain reaction. You've got two or more reactions that share a common piece. So, say you have a solid that doesn't really want to dissolve in water. Well, what if you add an acid? If that acid reacts with one of the ions from the solid, it pulls it out of the solution. And because of that, more of the solid has to dissolve to replace what was lost. See? One reaction is literally dragging the other one forward.
So as you can see, these three sections aren't just separate topics. They're all woven together. Lewis acid-base chemistry explains complex ions. And those complex ions can then play a huge role in a coupled equilibrium that completely changes a compound's solubility. It's a really beautiful system where all the principles work in harmony.
And that's our lightning review of Chapter 15. So I'll leave you with a question to think about. Now that you've got this framework for equilibrium, where else do you see it happening? I mean, it's everywhere, from making fertilizers to how our blood chemistry works to how the oceans absorb CO2. These ideas are fundamental to the world around us. Thanks so much for tuning in.